Bir class.
Okay, can you hear me now? Particularly just, great, okay, thanks. All right, you know, it's really weird, right? So you, Justin in particular, you actually heard me thinking very loudly that I should try and say something. Or maybe I was talking to myself and you heard me, right? I was probably talking to myself about it, but yes, okay. Hi, okay. So you guys, I keep missing this section of time, and I don't feel good about that. But I am, but I certainly can't. I don't want to ask you to meet at other times or something, or like to compensate that way. But hopefully, you will get a chance, or did get a chance, to see the video that I posted last night of the other section. Could any? Well, yeah, I don't. But I do want to sort of pick up from where I was with them. So, so we're gonna. Can anybody well, no, I don't really want to. Yeah, I would like to know, can anybody verify if they even saw that the video was posted of the 1050 section yesterday morning? I'm not asking you if you watched it yet. I'm not, and I don't like even to look to know particular, but could someone that's a yes? Great. Oh no, wait, that's a yes on the whether you could hear me, right? Could anybody verify whether that video, like whether you even found that video, whether you were notified of it, like the YouTube of yesterday's 1050 lecture? That's a no. Huh, okay. If I could even, can I even ask if, I wouldn't mind if someone would look right now. I mean, I know what it looks like on my end, but I never know what it looks like on your end in any way. I just want to, what I'm saying is that yesterday I taught this class at 10:50, but I didn't teach, but like we didn't, because I was a Monday schedule and blah, blah. I mean, yesterday I was supposed to teach this class at 10:50, but didn't, but then I taught it at 12:15, and I just want verification. And then I posted what we did. I mean, it wasn't an exciting class, and there was a lot of working individually, like, so you'd have to skip around, but at least, and then I also did send around the notes. So let's start with that. Can anybody verify whether they got the notes, like the PDF in the Google Stream? Okay, this is helpful. This is helpful. Thank you, Alyssa. Oh, great. Okay. Okay, and that's great, and really good. Because again, I'm never really trying to push harder to know exactly what you guys are doing in your time, because I think it's all very tricky. But I just want to make sure that whenever I can get out there to you, you at least have access to. So all right, so please do watch at some point what we did yesterday, because it was actually like a working through of the material, like a recitation kind of thing that might be helpful. But what I'm going to do, and it's in the notes that I sent, what I'm going to do right now then is do another warm-up exercise like I did with them, but we'll try to push this one step further. Okay. So here we go. Okay, this is really what we're doing right now, just to try to, okay, and I'm glad you got this. Okay, we are still here in 1D kinematics. So everything we're analyzing here in physics right now is motion of an object within one line of space. Like any object that has 1 degree of freedom can move back and forth, or you could call it left and right, or you could call it north and south. We call it positive and negative. But that's the larger situation of 1D kinematics. We are specifically concerned here with objects that are changing their velocity, but not changing the change, okay? And the key, and just to say really fast, the key, so that means from a calculus perspective, it makes sense. One way to just, because I'm going to rewrite I'm going to keep rewriting the equations over and over throughout the whole semester, next semester, like whatever equations we have going so far, I'm going to keep writing them. I'm going to ask you to keep writing them, because it never does to actively try to memorize them. It defeats the whole purpose. But if you keep keeping track of what we're saying so far and see the difference between definitions and recognitions, it helps. So I'm going to rewrite the equations that we're dealing with in a minute, and they are the ones that we're practicing with the exercise that we're going to do. But I want to point out that 2 out of the 5 equations are kind of just stating the connection between the material we're doing with calculus. Like you were all required to take calculus for this class. I have mixed feelings about that. You really will find that you really need to use the calculus in a very, very big, heavy, explicit way in physics 204. Okay, like it really becomes very explicit there. In physics 203, we do a lot of things here that you don't need to solve in a calculus way. Like your calculus tools, even though you are required to have them, they don't necessarily have to be sharp as a tack to do a lot of the problems I do here in physics now, because there's a physics way of doing them that connects through and uses all the calculus. But to be totally blunt, it's just as likely to learn calculus from physics as it is to learn physics from calculus. And so what I'm saying is we're going to, from a from a calculus perspective, everything that we're, and if you do feel comfortable with calculus, then this will make sense to you. What we're doing here is analyzing motions at the level of the second derivative. The basic point of train of thought and all the preliminary physics discussions we sort of try to have, even in a virus, it is to show us all that velocity, the first derivative of position with respect to time, is in the eye of the beholder. Well, I'll write it right here. Here's what. Okay, all the early stuff, early in this course or early in the history of physics, the stuff that we were doing that seemed more like English and like analyzing a train in motion or talking about the sun and the moon, the stuff that I'm trying to make more and more mathematical, looking as we progress through the material and stuff. But what's the point of all that stuff? Really, secretly, it's to build the calculus mindset, or it's to feed the calculus mindset and say ultimately, look, there's position in time. There's space and there's time. And anything that moves maps out some kind of function, some position time function in the world, right? If you move, we can always make a graph, a scatter plot of where you are at any given moment in time. That's a function. The first derivative of that function, velocity, or the first derivative of position with respect to time, dx dt, which is what we mean by v, that velocity is totally important. All of our equations are about it. It's what we measure and analyze and stuff like that. But it's relative. Velocity is not something that you can objectively feel, measure, or observe. That's actually what we're trying to get at when we say, like, you can say the sun moves relative to the earth, or you can say the earth moves relative to the sun, but you can't say actually, absolutely in space, the reality is actually one of them is sitting still or going this fast. You can't. Dx dt, the first derivative of position with respect to time, is not actually where the action is in physics. It's not, you can't feel motion. d2x d2 dt2, the second derivative of position with respect to time, acceleration, that is ultimately what we experience, feel, measure, and care about in physics, because it's linked to forces. And so right now, what we're analyzing is motions that do change their velocity, that do have a second derivative of position with respect to time, to characterize their motion. They do change where they are. They do change the way they change where they are. And they change the change in that, but they don't go any further. We're looking at situations where there's a second derivative, but no third derivative. That mathematically, that's what we're doing right now. And the equations, so I'm going to start us off with it. So we're going to do, and free fall. This is just a quick sum of a lot of things I said yesterday, is the naturally, and if you were there yesterday, if you were able to attend at 12:05, I apologize for this redundancy, like then you did hear me say this yesterday, but Okay, just to be clear, like, so our topic, our context here is a constant acceleration, which means a situation where there is a change in velocity, but there's not a change in that, even though there like could be, but that's not what we're studying. And the naturally occurring and highly pervasive case of A equals A naught, of an acceleration rate that doesn't change, is free fall near the surface of the Earth. That's the point. That's supposed to be the big takeaway of Lab 3. Is that you find, is not the number, but just that when things fall, they do have velocity, they do change their velocity, but they don't change the change in their velocity. They have some rate of acceleration, which turns out to be approximately 10 meters per second squared. And from here on in, we call that rate G. We give it a lowercase letter to express the fact that it is in fact a constant. It won't change. All right, given all that, that's too much. Here's the exercise we're all going to do, like in breakout rooms, or here's the problem to solve. Okay. Okay, I'm going to, ultimately, there may be more parts that we could add to this problem. Ultimately, in order to solve this problem, you may need to break it into a number of parts. In fact, I highly recommend that you do. But I'm saying right now, this is one problem. Of course, illegible as usual, I apologize. But I'm saying we throw an object, and if you really did it, if you were here yesterday or you watched, then in some ways, this maybe will be fast and easy for you, maybe. But maybe not. I'm saying we throw an object up at 80 meters per second. That's its initial instantaneous velocity. Let's assume that anything we call up is positive. I mean, you can actually change this assumption if you want, but just make an assumption and stick with it consistently. I'm assuming anything up is positive, anything down I'm going to call negative. That's my coordinate system. In that coordinate system, I throw something up at positive 80 meters per second. I'm near the surface of the Earth, so in the wake of Lab 3 and stuff like that, what I know is that things always accelerate down toward the surface of the Earth. They always accelerate at a constant rate that we call G of approximately 10 meters per second squared. Like you could say it's more like 9.8, but even that is an approximation. So, so this is just as good. I'm calling it negative because I'm assuming that down, because I'm calling down negative. These are the facts. You throw something up at 80 in a gravity field near a planet where things accelerate down at a rate of 10. My question is, how high does this thing get before it starts falling down again? Like it will get to, and there's nothing else going on. There's no air resistance. There's no tricks. There's also no other facts that you need. We throw something up at 80. It's going to go up for a while. It's going to reach a peak height and then it's going to fall down, and it'll fall back down. Say it was thrown up from the ground, it will fall back down to the ground. If we're standing on a cliff, it would fall even lower. But what I want to know is, how high does this thing get? I want you to do anything you can to get that answer. I'm asking all of you. I mean, I'm going to shut up in a second, but this is the problem that you're going to do. I will put you in rooms in a second. For some of you, this might be a joke. This might be one step in your mind, but then I want you to explain that step and break it down and convince the other people in your room. And for others of you, it will be more work. You can use equations, which I will remind you. I'm going to write a whole list of equations again in a second that you, I don't know how you see them in the breakout rooms or whatever. Or you can do what you just saw. You can look at the notes. That would actually be the most useful thing. Definitely look at the notes from yesterday, even if you haven't had a chance to yet. And you'll see in the notes that I recommend making a chart that looks, that's set up something like this. And even this may be illegible, and even this might have answers in it, but you don't get bogged down in looking at the particularities of this chart. But I just made one. I recommend you make one as a way of thinking through the problem. You can even make a graph. Most people hate making graphs if they're not asked to make one, but do whatever you need to do to get the peak height of this thing. Again, if you think you already know it, if you figured it out by the time I was already talking, then your job is to really get the other people in the room to, first of all, believe you or agree with you. And then second of all, then to show them how to do it. Like, if you really believe you have the answer to this already, then basically what I want you to show the other people in the room is that you could also get the answer, even if the question was thrown up at 100 meters per second. Okay, like you should be able to do it regardless of the number. And I'm praising you in advance to any of you who already have an answer to this. But the question is, it may or not be easy, but it is simple to state, and it may or may not take you. The question is, something is thrown up at 80 meters per second, and it necessarily is accelerating at a constant rate of -10. How high does it get? Okay, that's the question for everybody. I want to put you in breakout rooms. The question is, how would I get these equations? Indulge me, assuming that, have you had time to copy this? And you do need to copy this problem if you can't hold it in your head, because it won't go with you to the breakout rooms. All right, I'm just going to take a stab and go to the next page and write down equations. Well, no, you know what? They're right at the beginning of the notes. I will, but I don't want to stall these breakout rooms. In my mind, we have a total of 5 equations so far. They're in those notes from yesterday. We have a total of 5 equations so far. In my mind, the first 2 are definitions, super important and useful. The next 2 after that are also definitions, triple equal signs, also super important, but not useful. I'm being honest. Like, of our 5 equations so far, the only ones that you really directly use to solve problems like this are 1, 2, and 5. And if you are using equations to solve this problem, you're going to find you have to use all of them. If you're only using some of them, you're doing something incomplete or wrong. So you're going to have to invent minor steps to get to the final answer of this, probably one way or the other. But this is the question. I'm going to shut up because I'm boring myself. I'm going to put people in breakout rooms right now. So please, once you get assigned, go. And I'll come around and visit and see what's going on. It's easier to talk that way. But please, once you get your assigned breakout room, go. And once you've copied down this is the problem. Like, take it with you to the break. Yes, okay, you got it. Thank you. Awesome. Thank you. Thank you. Thank you. Awesome. Yes. Okay. Okay. Awesome. Hello, Lydia.
Hi. Yes, there is no one in my breakout room.
Lydia?
Can you hear me? Hello? Can you hear me?
Hello. Sorry to inter. Hello, Armand. Hello. You could take mute off, by the way, if you have a second, or Armand. Or...
Hello? Can you hear me?
Wait, Armand? Hello?
Yeah, hello? Hello?
Oh, hello. Hello, Armand? Aaliyah? Lydia? Armand? You guys? Hello?
Hi, can you hear me? Hello? Hello?
Okay, you can hear me. Okay, can you guys please try one more time to go to that breakout room, because Armand was there waiting. I was trying to talk to him, but he was by himself, so I couldn't talk. Can you just try to go back to that breakout room, both of you, Aaliyah and Lydia? This is weird. Okay, thank you. I appreciate it. I appreciate it. Okay, thank you. Thank you. I appreciate it. Thank you. Okay. Mm. Hello, sorry to interrupt. Can you guys hear me?
Yes.
Oh, maybe I can't hear you. Wait, is that my problem? Oh, wait a minute. Can one of you say something again?
I
Uh,
can hear you.
Oh, okay. Okay. Thank you. Sorry to interrupt. I've been having a big problem with another room, and now I see that the problem was on my end. So I don't mean to interrupt, but are you guys okay? Do you want more time? Are you totally done? Are you in the middle of a disagreement? Can I do anything? Or should
I'm not sure if there's anyone on the other end. I tried saying something at first, but
Oh, so you've been here alone. Oh, so you don't. So I'm the first conversation you've been here alone, as far as you can tell.
yeah, I'm not sure if Andrew's on. I tried like saying something at the beginning, so
Okay.
I didn't have anyone, but I was attempting to do it, but I'm kind of lost. Like I'm not sure
Oh, okay.
where to go with it.
Okay, no, that's very fair, and this is helpful. And again, I'm still finding all this very awkward, and I'm sure, so I don't mean to make it awkward, but that knowing all that, just now that I know that there's like been technical problems of this kind in each room, but knowing that you've got the problem, but you're stuck at it, I think I'm going to bring everybody back. And like, thank you for telling me all that. That makes total sense. Just hang in. I'll bring everybody back together, and I'll explain them. But in other words, if I explained the problem now, you would not be wasting your time. Is that a fair thing to say?
Yeah, I think it would be better to explain it a little more, because I feel like we've only gotten like a few little things in lab that have helped, but like to get like maximum height, I don't think we've really covered that. So I think that's where.
Oh, right. Oh, well, no. Well, just to be honest, well, fair enough. All right. No, I definitely see that it'd be better if I explain this. So I will. I'll bring everybody back and I'll explain it. But I will say it's meant to be the first time. Like,
Okay.
I do agree that you've never heard the word peak height before. That's totally true.
Mm-hmm.
It's not like we've ever even pretended to teach like how to do a peak height problem. But I think what I'm saying. But no. So you're right. It's more like. But okay, I'll bring everybody back and I'll explain.
Yeah, no, because I know lab, like she said that we would be ahead of lecture anyway, so I wasn't sure if we were supposed to like cover some of this because we're doing the ballistic projectiles, so I wasn't sure if maybe we're supposed to use something from that to kind of figure it out.
Okay, this is very helpful. And the answer is no, you're not. You don't have to use something from that. I could totally see why you would seem like you do.
Yeah.
It's only going to use these equations, but no, okay, what you're telling me is totally helpful, and I appreciate it. And I don't mean to put you on the spot, but.
No, it's okay.
Okay. Okay, I'm going to bring everybody back together. This is good. Thank you very much. I appreciate it. And thank you for having a picture. I appreciate it.
You're welcome.
Okay. All right. See you. Okay. Hello. Okay. Hello, everybody. Okay. Welcome back. So I got a chance to visit some of the breakout rooms, and I've learned a lot by going to these breakout rooms. I've learned a lot. I can see why you guys hate them when they don't. I mean, one of the rooms just now had all these issues, and I didn't even realize until after I left the room, and I want to apologize to that room, I think it was room 3 or something, that they were thinking their mics weren't working, but the entire time my speaker wasn't even on. So all the non-communication was a total fault on my end. And then I went to another breakout room, and someone was missing from there, but someone was or at least electronically missing, but someone else was very honest about where she was in the problem in her head and what's going on in lab and stuff. So I could totally see, so if no one's gotten an answer to this problem, first of all, then I'm not surprised, and nobody should feel anything bad. If nothing else, these breakout rooms just now served as a good way of bringing me up to speed of where everybody's at mentally, and also how tricky this can be. Like the breakout rooms, I think really, really work if there are really 4 people in a room who can communicate with each other and find each other. But there's like a lot of reasons why, even in good faith, that doesn't always happen. All right, so I'm going to explain this problem, is what I'm saying. You have to understand that I need you to understand that from my perspective, I'm so afraid of boring people or explaining something that they already know that I could tend to go in the other direction accidentally. It's pretty clear to me now that I should explain this problem or how to solve it, so I will. But I also do want to make it clear, like, because this is physics, and we'll do whatever we need to do to get physics straight as we go. We all will. And it's all about depth, not breadth. It's all about depth mastery, not speed, and all of that. So like we could work on this problem all semester. And if I felt by the end everybody really, really, really got it, then I would feel like you've learned physics and I've taught you. Like, it doesn't matter what problem we're working on. But let me also make clear at the same time, the reason physics is like that, why you can work on something forever and it be okay, not even go into step 2, is that, oh yeah, all the pieces to solve this problem are there already in your brains and in the notes. So like, I do want to make clear that this exercise that I'm giving, whether you call it an exercise or a problem, is I'm not expecting that you're drawing pieces of how to solve it from lab directly. Not directly. I'm not expecting that you need other equations that I haven't given you or anything like that. Like it is just the next exercise from what we did last Wednesday. Put more directly, it should be solvable from nothing but these equations that we've discussed so far, as long as you break it into steps. And again, I think really only 3 of these equations. That doesn't mean it's easy, but it is the next step. Like we haven't skipped anything, put it that way. But okay, so I'm just going to talk it now, and forgive me, but I'm gathering I think that might, but stop me as I'm talking, please. If nothing else, all of you, whenever I do talk to you one-on-one, it is clear the best thing, it's not about you ever saying something right or wrong to participate. The best way to use your participation in this class, all of you, is to use your participation to control my speed. Like, think of your job as not showing me whether you know right answers or wrong answers. Because if you worry about that, then you'll be worried and never say anything. And honestly, I'm not worried about that. But your job is to say things to let me know whether I should be going slower or faster at any moment. Honestly, like if you're ever thinking about whether to interrupt me or raise your hand, anything you can do to control the speed of me so that it's best for you and for the class is really is physics worthy work, if that makes any sense. But okay, so I'm gonna solve this problem. Again, the exercise was, right, I'm sorry. Right here on the board is all the equations. Again, just while I'm babbling stuff, it never hurts to recopy and see if you can write them without looking and see if you understand them, blah, blah, blah. But I'm gonna use these 3 directly in order to solve the question at hand. And the question at hand, again, and tell me if you want me to go back or whatever, but again, the givens of this question are very simple, just meaning straightforward to say. The givens are or also, by the way, wait, I didn't visit all the breakout rooms, so I'm also being obnoxious. There may have been something, if anybody wants to say anything, I mean, either volunteer, if you do think you have the answer, like some people might have answers, I'm sorry, or even thoughts. If anybody wants to say what they did as a first step or something, please interrupt me, or please just turn off your mute and say it. But yes, and I'm looking, or say it in the chat or something. Okay, we're going to solve for what we can call y max, or you can just call x for, like, we're solving for a displacement. I'm calling it y max because I'm going to use y instead of x for up and down, I suppose. And I'm looking for the maximum y. But it doesn't matter what, we've never seen this before. It doesn't matter what I call it. I could just call it x, but this is the question, right? And I'm going to have to break it down. I can't answer this in one fell swoop. I mean, I can. Actually, I think the answer is 320. If anybody wants to know, I think the answer is 320. I can do it in my head, but even in my head, when I'm doing that, I'm doing a bunch of steps and doing them fast. There are steps that I'm doing. So what is the first step that I'm doing? The first step that I'm doing is I'm gonna say to myself, like, I'm asking what seems to be a fair, like, you could imagine that there should be a way to figure this out. Like, physics should know the answer to this. And I'm using the phrase peak height because I think we all know if you throw something up, it will reach a peak height and then come down. Like, nothing goes up and up forever. But I've never used the terms peak height before. So it's really fair and easy to think, like, was there a homework problem on peak heights that we made? Like, was there a PowerPoint presentation or a lab or something on like peak heights? Like, how do we solve a peak height problem? But what I'm really saying is, well, peak height is just an English phrase that, you could be faced with a new English phrase at any time. But what does peak height really mean? In physics terms, it means we're solving for the height when the object stops going up and starts coming down again. When the object stops going up and starts coming down again. In other words, what I'm looking for is the height where the object stops, where the object reaches a velocity of 0, which I really do believe is what happens when you throw things up. And maybe that is a surprise. I think it was a surprise when I first thought about it through for the first time. But if you throw something up, it's going slower. It's losing speed as it goes up, just like it's gaining speed when it comes down. It's losing speed at a rate of 10 meters per second every second. It eventually runs out of positive velocity and starts going into the negative velocities. That run out moment is the velocity 0 moment. So what we're looking for y, or call it x or whatever, but when v is equal to 0, right? That's where, right? And if I could have reached, in physics terms, what I'm really asking is, how far has this thing traveled by the time it achieves an instantaneous velocity of 0, assuming that it started with 80, right? I still don't necessarily, is there an equation for that? I don't think so. I agree. There's not like an equation for this. There's no equation that links directly, there's no equation that links y or x to anything except for average velocity, right? Everything, and this doesn't say anything about average velocity, but average velocity is always the first step that I always have. This is what I was trying to say last week. No matter what anybody asks you, the way you're going to get at it is through average velocity, because that's the simplest, most reliable definition we have, and it's the simplest thing to measure and picture how far something gets per time. This thing here relates displacement to instantaneous velocity, the sentence that I wrote down here. In other words, we're looking for the place when the object achieves an instantaneous velocity of 0. Not, by the way, notice, we're not looking for a place where the average velocity is 0. Like, I don't know what that would mean. If the average velocity is 0 for a while, then things not moving. I'm talking about one moment when it's 0. We're looking for that location. Now, I don't know what that location is. I don't even know how I would go about finding it. But notice the English I just wrote down. We're looking for the place when I don't even know if that's actually English, but we're looking for the place when v equals 0. So wait a second, maybe I could think of it that way. Can I back up a step and ask myself, how much time will it take for this thing to run out of speed? If I could get how much time it takes for this thing to run out of speed, if I could figure out, honestly, when the object reached a peak height, wouldn't I just be a step away, or wouldn't I be a lot closer to knowing where the peak height was? I think I can do this. I'm saying, I'm going to solve for time to the peak height. And I think this is something I can get in one step. And by the way, well, okay, here's one of the three equations. It is the definition of average acceleration. This whole problem is about acceleration. There is an acceleration, it is constant. And look, it's one of the facts that I have. I have the acceleration, I know, I have the initial velocity. That's what was given to me, the problem of positive 80. And I'm looking for the time at which the final velocity v is 0. So I actually have everything I need here to solve for the one unknown of t. So I'm going to rearrange it. Well, right? Okay, and v final. So I'm looking for the time at which this object achieves a velocity of 0. It started with a velocity of positive 80, right? So it's like minus a positive number. That minus is there because of the equation, not because 80 is a negative number. A is the negative number of 10, right? So, and by the way, units wise, well, here, let me just fix the units. Let me put the units in. It's not a mistake. If you already, it's not wrong. I'm just putting in the units. If you think about the units work. So what I'm saying, now this is not the answer yet to the question. We're almost at the answer. And in fact, I think with this information, I'm going to turn it back to you guys, the class, and ask you to go the extra. I think you can probably get the answer now, or at least but anyway, this is not the answer yet. This is one piece of information that in my mind would be very helpful to getting the answer and would be a good way to start. It is not the only way to start, by the way, but which is super important to realize, but this is a start. What I just found out is that in 8 seconds, this thing will reach a peak height. Now, if you back up and look at the numbers, some of you might have already guessed that already, and many of you might have quickly guessed it. If you asked yourself this question, if you were smart enough to break down the big question into smaller questions that you could maybe even approach, which is what we have to do. If you thought about this question, you might have even saw the answer in your mind and then maybe even rejected it because it seems too easy or something like that. But this 8 is there for exactly the reason you think. It's not a coincidence. Like we threw something at 80, it's losing 10 every second. So how much time does it take to run out of speed? It takes 8 seconds. If you had 8 eggs in your pocket and you lose 1 egg a day, it takes you 8 days to run out of eggs. We literally did just divide 80 by 10, as you see right here. That's that's not a coincidence. It's the logic of the equation. The equation isn't really a formula. It's just a definition. It's just a concept of acceleration. The concept is your rate of change of speed per time. So if you start with 80 units of speed, we're saying, then you know right away, or once you get used to this, if someone says I threw something up at 80, you right away can see in your mind, once you get used to this, oh, okay, 80, that means it's going 80, 70, 60, 50, 40, like in terms of speed numbers. Slowing down, it'll take 8 seconds to reach the top. Okay, by the way, that also means it's going to take 8 seconds to come back down. If we put this all into a chart, that's what we'll find, as you would expect. But before we even go there, what I'm going to do is shut up. I say with that information or with that kind of thinking, you can now, if you're just careful with the concepts or the other equations, you can go the next step or two and figure out how high it must travel in 8 seconds. Like, you know its initial speed, you know its acceleration rate, how far will something that travels at those rates get in 8 seconds? Like I'm saying to everybody, that's the next step, you can do it. But I also want to say, to not even let you think, I also want to say, if I were in your shoes or when I'm in your shoes, even if I saw all this now, if I didn't think of this before, if I saw all this now from Yaverbaum and then Yaverbaum was like, okay, now do the next step. See, now you can do this on your own. I would be like, all right, but I wouldn't have known to start it that way. Like you're making a convincing argument, Yaverbaum, maybe that like, why don't you break the problem down into this mini problem and do this first? Like that's convincing, but I wouldn't have known to do that, or I would have chosen a different mini question that I'd be stuck on. my true advice, and that's fair to worry about that, but my real advice is this isn't the only way to start it. There's a couple, the way to start a problem, because everybody always asks, like, I don't know how to start the problem. I could do it once you get me rolling, but I don't know how to start. The real way to start is any old way at all. Like the real way to start is just do stuff, and the stuff will either lead you somewhere or it'll make you realize that it's the wrong stuff and you'll try something else. I think you get my point, but you got to be willing to write down stuff that might turn out to be wrong or that you might throw out. That is the key secret that great, strong science students are always dangerously not realizing. Like you have to be willing to be wrong in public, and you have to be willing to be wrong on paper. And here, paper doesn't mean public, luckily, that's the way to start, is like to do something wrong, and then you'll realize it's wrong, and then you just say, anyway. So I'm asking everybody, take this information now, 8 seconds. How high will it get that time? And I will warn you, if you do this too fast, you will get it. There's a way to do this with confidence and get it wrong. There's a way to be insecure and not do it at all. Just be careful. Like maybe I'll even say this. Well, no, I won't say anything. Yeah, just try to get, if I'm telling you it's going to take 8 seconds to reach the peak height, all of you, I'm not going to put you back in rooms, but just try do something now to turn that into a distance, and feel free to say something or put it in the chat if you have a question or a statement. Oh yes, and I guess any thoughts at all? And I now realize I actually did say the answer before. I don't know if anybody caught it, but I don't know if that either was encouraging or just any thoughts at all what to do now.
Would you use the velocity, and then since it's 80 meters per second and it's 8 seconds, you would multiply them?
Okay, thank you. First of all, thank you totally for saying anything. And yeah, okay, now we're talking. I'm going to add one thing to that, but yes, this is what we have. Okay, absolutely, good. I mean, strangely, the answer is going to end up being, the answer is going to end up being 320. But yeah, the first thing Alyssa's saying that's so right is, look, we've got a time here. We're looking for a displacement. The only link could possibly be velocity. Like we have to use the velocity now. And this is the one thing that everybody kind of knows coming into the class in a way, is like distance equals rate times time. But we're saying in class, the real thing about physics is, well, distance equals rate times time, yes, but there's tons of different kinds of rates in the world. So you have to be careful. Really, distance doesn't equal any old kind of rate times time. Distance equals average speed times time, and displacement equals average velocity times time. In other words, I'm going to use the velocity, and I'm going to remind myself, I'm going to use the very first equation and say, okay, average velocity equals displacement per time. Therefore, displacement equals average velocity times time. So yeah, and I've got a time, and I'm looking for, and by displacement, I mean how far something gets, like the initial place where this thing started. There's no reason not to call 0, like wherever this thing started, I'm going to call position 0. We put our coordinate axis, so everything above it was positive, everything below was negative. So displacement equals average velocity times time. We've got the time, we're going to multiply it by the average velocity. Now here's the one thing though that I'm going to add to what Alyssa was saying, or the one cautionary aspect is displacement equals average velocity times time. This thing, on average, was going up at some velocity. What was that velocity? I don't think on average, it was 80. And I'm talking out loud, not just to, but I'm saying, I'm going to do this, but I'm not going to plug in 80 for V. I mean,
Would you, sorry,
oh, sorry, go, please. Sorry. Please.
would you use like I think it was the fifth formula, but it's the third one you gave us. So it's average velocity equals V initial plus V over 2.
Yes.
So then
Oh,
it'd
you
be
just made my
40.
day. Yes, you just made my day. You just suddenly made this feel like, well, not just suddenly, but no, okay. Yes, thank you for
Okay,
making this
that
feel like
makes
a,
sense. That's how
A
you got
faster?
320.
yes,
Hi.
yes, you're exactly right. But then I just heard somebody else. Yeah, no, that's
Yeah,
exactly.
I did that equation,
Oh,
the
good.
average velocity, and I ended up getting 40 for that when you find
Right.
the average velocity, and then you plug that in to average velocity equals x minus x0 over t, and then you get 320 from that.
Oh, yes, yes, totally right. So you agree. So
I
both of
agree,
you.
yes.
Yes, well, both of you just made my day because you're totally right. And yes, and it makes it feel like, yes, that's exact. In other words, we're saying here, and this is, and if you get that, I'm not saying that physics never gets harder, or I'm not saying that that didn't feel hard 5 minutes ago, maybe, but the key that they're both getting, well, I'll write it down, but in a second, but the key that they're both getting is there's a difference between average velocity and instantaneous velocity. And we need to juggle between both all the time. And put another way, there's a difference between well, yeah, there's a difference between average velocity and instantaneous velocity. Um, one is much more useful to use, but it's much harder to get. So anyway, yes, what they are both saying is, okay, we need to put, we know that the time is 8 seconds, but we need to put the average velocity here. And the average velocity is the average. The average velocity we can get by literally averaging the beginning and end velocities, the 80 at the beginning and the 0 at the end. We're literally just averaging them together according to this equation. But remember, we're only allowed to do that. So we're using, this is where we're using all 3 equations. We're using average velocity by definition is displacement per time, but also if and only if, remember, if and only if acceleration is constant, we can also say that average velocity is the average of velocities. Like I'm just trying to tell everybody, notice we are using 2 different average velocity equations to solve the same problem. We're treating it 2 different ways in the same problem because we have to, and because we're allowed to. Like we are averaging 2 velocities in order to get the average velocity because we can, because the acceleration is constant. Hold on. So yes, we get 40 here, 40 meters per second. I'm gonna have to turn the page now later. Tell me if anybody if you want me to go back. But so we're saying. Okay, so yeah, that's great. That is the answer. So that's, this thing goes to a peak height of 320. Any questions from anybody else on that? So like, it obviously is just an exercise, but it's trying to, because I'm gonna push it further then. Let's say if we get that. Still the same example. Okay, still assume the same givens. Let's just push it forward. Sorry. This is maybe plug and chug, maybe not, but I want to know. Well, here, wait, one thing. Okay, two more questions about the same situation, and hopefully it'll get clearer and clearer. But what I want to know now that so you notice when I ask a question, you might have to invent other questions for yourself in order to answer that one. I mean, but it's all a matter of watching your own brain work backwards. Like if I ask, "What is this?" and you start sitting down, okay, I'm going to try to get what he's asking for, and then you're like, "Oh, I can't get it. Wait, this is confusing." What you want to do is say like, "Wait, why is this confusing? Why can't I get it? Oh, I can't get it. It's confusing and annoying because even though he's asking for blah, I would need blee, or I also don't know blee." Well, then say, okay, I'm going to set out to find blee now. Like assume it's a multi-step adventure, in other words. But what I'm asking then here is, all right, at a number of different moments, I want to know what's the exact instantaneous velocity at that moment. Velocity. So some of these answers might be positive, some might be negative, but I want to know how fast it's going at the second, at the third, at the 14th, and the 15th. I'll tell you right now, I'm assuming that it will be traveling for that many seconds because I'm thinking if this thing is going up for 8 seconds, I think whether I made a chart or a graph or watched the rest of the movie in my mind, if it's going up for 8 seconds, I think it's going to take 8 seconds to come back down to the ground. I think that whatever patterns of speed loss I witness on the way up are going to be repeated as patterns of speed gain on the way down, because the acceleration is a constant. Because no matter what's happening, this thing is always losing 10 meters per second of velocity, always losing 10 meters per second of velocity, whether that means going like to lower and lower positive numbers or heftier and heftier negative numbers. It's always losing 10. So I want to know V at those 4 moments, by whether it's equation or logic, however just you want to do them. Then, as just one example, once you know various velocities like that, tell me how far this thing has gone within the third second, like from t equals 2 to t equals 3. I could just as easily ask how far I could just ask how high is it at the third second, and I probably will ask that, and you probably want to know that or figure that out. But if I ask how high is this thing at t equals 3, that's actually the exact same problem as asking how high does it get in 8 seconds. Like, I hope we could get that now because we just did that in effect. But I'm asking something slightly subtler. I'm asking how high, by how much does it increase its height, or how far does it get just in that previous second from t equals 2 to t equals 3. Anyway, I'm going to ask everybody to do this now. I'm not going to put you in the breakout rooms right now, but we have like 8 minutes. So just try your hand as individuals on this, and I'll tell you the answers and then we'll go. But I would encourage, if anybody has anything to say, even already, like, please do. I mean, whether it's a question or a thought about how to do these. Again, I don't think you need any new equations to do this. You don't. But one hint, well, not a hint, but just remember, I mean, if V naught is 80, that means at t equals 0, V is 80. So I want to know what V is at t equals 2. If you could just make a chart or something like that. But does anybody have any thoughts of what is V at t equal 2? Okay, how about this? Can everybody hear me right now? Raise your hand. Could you give me an electronic hand or something if you can hear me at all? Awesome, thank you. But that's 1, 2. Okay. Wow, I'm losing people by the dozens. 3. Okay, yes, you can hear me. Okay. Again, just everybody, this is like the control in the experiment. Can you just keep your hand up if you can hear me, please? Or yeah, okay, thank you. So so assuming you can, cool. Oh, it says down there on the bottom. Okay, so I'm asking right now, and I know we have like 5 minutes left, and I know it is what it is, but like if at t equals 0, V equals 80, I want to know right now what is V at t equals 2. Like, in other words, this is a situation, right? Like if we're making a chart, like right now, I'm not even asking, I'm just asking about velocities, not about displacement. So what we know is we got something that starts at positive 80 of speed, units of speed, and loses 10 every second. So if anybody had to predict if I can get what's going to be what's the next entry in this V column? Like it starts at 80, 1 second. Yes, thank you, Justin. Yes. Yeah, thank you. You just breathed life. Yes, and that's all I wanted to know. And this means class can be over in a couple of seconds. Yes, exactly. You the man. This is literally what this pattern means. Right, and then what happens after, I should have made more room, but what's going to happen after the 8 second? It's going to go down to -10, -20. Like this is what free fall means, or what constant acceleration means, especially, well, this is what constant acceleration means. It means change in velocity. It means you're losing 10 units of velocity, whether your velocity is positive or negative. And that's why it like works. That's why when things go up, they eventually come down. And while they're going up, they're slowing down. And while they're coming down, they're speeding up. It's all one consistent pull the whole time. So I think the answer, I'm going to just write down the answers to my exercise, and then we'll split. And you've all been very kind and very indulgent as always. And we're moving along. And people are starting to come for the other class. That's weird. But let me just write down. So my answers to this exercise right here. And if you want to fill out the rest of that chart, you can look back in the notes and see how we did it. You could do it for any number, but how we did it yesterday. Answers. Sorry. And if you just continue down that chart or use reasoning, you realize I asked for 2, 3, and I asked for 14 and 15. That's just the same moments in time on the other side of this round trip, right? In other words, oops, sorry. Sorry. And I know we're about to go, but one last thing, maybe the hardest, what time is it? Okay, we have 1 minute. When I asked how far, oh, but how did I get each of those answers? I'm sorry, just one thing. If I want to know how fast it's going at any moment, how fast at any moment, if you want to think of it in equations, what I'm doing every single time is this, but just rearranging it to say this. Right, at any single moment, the velocity is whatever it started off, v naught, plus whatever it lost to acceleration. Like, that's what I'm doing to figure out those answers. But lastly, and I know I'm going a little fast right now because it's the last minute, but I will publish the notes and Very lastly, though, if I want to know from t equals 2 to t equals 3, I wanted to know how far, right? That's a slightly subtle question. Well, I need to know the two velocities. That's why I asked them a second ago. Like at t equals 2, v, you said, equals 60. At t equals 3, we said v equals 50. Why do I care? This is the last thing we're going to write down. This is the last thing we're going to say today, but it's exactly what like Alyssa and Justin and Aaliyah and someone else did for us. Oh, and I know someone else did for us a moment ago, which I totally appreciated. It's the same exact method. I'm going to say, oh, if I'm looking for some interval of time, how far something got, I've got to say displacement equals average velocity times time. Displacement is average velocity times time. What's the average velocity here? Well, since acceleration is constant, I can average the velocities to know. I can say the average velocity equals the average of these two velocities, which is 55. So in the 1 second between t equals 2 and t equals 3, something traveled on average 55 meters per second. So it traveled 55 meters. And that's the last answer. And I'm going to hop off right now because the other class is coming in. Sorry about all the life. Just keep wherever you are in the homework or wherever, just do the next thing. Just and look back in these notes and just try to compare it to it. Just understand it's like a video game if you've ever played them, and I never did until I did. But no matter how hard any next step is here, or no matter how much time goes between our meetings, anything we're asking you to do next is actually based on whatever you have in your notes from before. Like it often will seem like you don't know what to do, or but I promise you the next step is always is the next step. And it always is doable from whatever you did before. So wherever you are in the homework or wherever, just keep going from there. I'm going to, oh wait, I'm gonna look in the chat and then yes, I saw the show. Okay, but thank you, those of you, and thank you for the participation, for real. Okay, I'm hopping off, going to the other class.